Good morning, everyone. Today we have one of our own, Ozgur Oguz. So Ozgur received his BS and MS degrees in computer science from our university, and he did his PhD studies on robotics at the Technical University of Munich. And he's currently a postdoctoral researcher at the Machine Learning and Robotics Laboratory at the University of Stuttgart. And he's also affiliated with Max Planck Institute for Intelligent Systems. And today he will talk about physical reasoning in autonomous robots from perception to action. The stage is yours, Ozgur.
Thank you for the introduction, and thank you for the invitation. I am humbled and also excited to talk about my research. So today I will be talking about a subset of my research studies that I worked on during my postdoc in the last almost 2 years. These studies tackle physical reasoning problems with a focus on robotic sequential manipulation tasks. And such skills are definitely not unique to humans. As we see here, like many other animals, a couple of badgers are capable of planning a sequence of high-level actions. For example, climbing the gate, loosening the wire, and pushing the lock to eventually open the gate. And they also collaborate to do that. They not only plan such sequences ahead of time, but they also control their emotions to carry out those tasks. So it's clear that they can also discover novel ways of using objects as tools to solve whatever problem they have at hand. And it seems this is mostly about escaping their prison most of the time. But what is the underlying system that enables us and such animals to construct and utilize these capabilities? Neuroscience and motor control and many other fields as well offer a system architecture where perception, action, and feedback loops are integrated and working in harmony. However, there isn't any principled approach and formalism yet that can endow autonomous robots with similar skills. Actually, I don't want to sound pessimistic or be overcritical. In contrast, I think we have the tools that can provide us with the initial stepping stones to start realizing this ambitious goal. For example, for perception, we now have highly advanced and effective data-driven methods in machine learning and deep learning. We also have novel methods like generative models or self-supervision to overcome the knowledge acquisition bottleneck that is critical. That's a critical problem for many classical AI methods. For me, though, I would like to position those formalisms as pattern recognizers and or function approximators, which is not a bad thing, actually. It's just to acknowledge how they might be exploited in autonomous robot planning settings. And on the action side, we also have highly effective and a broad selection of rigorous formulations from graph-based search to Bayesian approaches for decision-making. And similarly, for the motion planning, we have well-established and studied sampling-based approaches along with highly computational, highly effective constraint-based constraint optimization formulations. And last, for the feedback component, there is a huge literature on control theory, and again, highly studied and rigorously studied and well understood methods like robust control or model predictive control, among many others. And here I also list reinforcement learning, again, as I see its usefulness in such settings. So as I said, I am actually highly optimistic that we have the tools to start off. It is just identifying the core challenges in integrating these seemingly different lines of research. For me, this starts with investigating how to construct representations from sensory signals and how to decompose sequential decision-making tasks into solvable sub-problems. And last, how to effectively use learning methods to adapt to the environment while also robustly controlling the motions under uncertainty, especially in the real world. So with this motivation, before I start explaining our initial steps in that direction, I would like to first introduce a work which is actually conducted by my postdoc supervisor, Mark Toussaint, just a few years ago, and it got the Best Paper Award at RSS 2018, just small advertisement. The main motivation was to develop a formalism to solve robotic manipulation problems that require not only sequential decision-making, but also effective tool usage given a goal. So here, for example, the goal, we see such a setting where the goal is to touch the red ball. So, which is actually out of the reach of this poor guy. And thanks to this beautiful formulation, the robotic agent figures out not only to use the stick, but also where to grip it so that it can still execute the next action, which is pulling the ball, for example, with the hook-like end of the stick. And we see different variations of such intelligent tool usage solutions for slightly different problems. So what is behind all this magic, basically? And the novel idea here is to formulate this combined task and motion planning problem as a nonlinear program, basically a constraint optimization problem, and which we usually within the group refer to as logic geometric programming. So in the rest of the talk, I will not go that much into the details of such mathematical formalisms, but I believe to understand and also appreciate the studies that I will be presenting today, I think getting an overview of LGP is highly critical. So I would like to quickly explain the details, but feel free to interrupt me if you have any questions, because this is really critical. As I said, for these combined task and motion planning problems, we formulate this as a constraint optimization problem, where we have a cost function that is a function of the state, not only the physical state, but also it might be a function of the symbolic state, and we have a final cost. And this optimization problem is constrained first via the initial conditions and also the final goal condition. And we also have path constraints that are basically the constraints on the motion plan of the robot. And these could be equality constraints as well as inequality constraints. And last, we also have switching constraints. And this is one of the critical components, actually, since robotic manipulation tasks involve physical interaction with the real world. That means we have to capture these kinematic switches accurately and effectively. For example, when we reach out to an object to grasp it, basically we need to contact with the object first. So these switching constraints explain or formalizes such situations. And as the last component, we also have logic constraints, which are nothing but first order logic formalisms. So these logic constraints allow us to search over the high level action space, like how to sequence the high level actions, basically. And as you can observe, these logical constraints or logical states might also impose constraints on the motion trajectory or also the cost function that we try to optimize. So with this formalism, what do we want to achieve? So we need to understand the deficiencies or drawbacks of this formalism, even though it's really beautiful. First, one is that we need full state knowledge, as all these objectives and constraints rely on this full state knowledge. However, for providing full autonomy, I believe we need to investigate representations that can be acquired via sensory signals. And also, I talked about this high-level decision-making for which we need to do search over the high-level action space. And for this, we might have many actions and many robots, and we might need to do several number of decisions, sequential decisions, and their combinations basically create a bottleneck in terms of combinatorial complexity. So for this, I propose to investigate decompositions of problems. How can we decompose the high-level tasks? And how can we decompose the motion planning tasks as well? And last, but definitely not least, such manipulation problems are high-dimensional, highly nonlinear, and non-convex. And especially if we consider the real world, where we would have uncertainty, we need to rely on learning and control methods to tackle these difficulties. So given this background and motivation, now I would like to first talk about a couple of studies where we take the first steps about how to acquire such representations. So for the first study, yes,
I have a question. Like, so in the previous slide, like, so how do you do the mapping between like what I will call like sense, perceive, act cycle of human being, like sensory motor cycle, with this sub parts like representation, decomposition, learning? Like, how do they fit into that cycle, like sense, perceived, act?
Mm-hmm. So now I don't have a full architecture, to be honest, so I just motivated, but the initial steps we took are integrating those individual components into our constraint optimization problem one by one, and eventually to combine them together. So for example, in the next couple of studies, I will explain how to acquire these representations and then integrate them into our nonlinear program. So this is our initial steps, and hopefully all of them will be based on the same underlying structure.
Okay, I'm looking forward to learn more.
Okay, yeah, I hope it will make more sense. So for this representation problem, first, last year we looked into pretty standard robotic manipulation tasks. Here we take the example of grasping a box, the target box. This is the green box, and the yellow box are just obstacles. So we just create a cluttered environment. Again, we have two pillars. One is a symbolic domain, where we define the first order logic-based action space, where each action has a precondition and a postcondition that allows us to do efficient search over the symbolic domain. So with this, we can figure out the discrete action sequences and feed them into the motion planning architecture, which is this nonlinear program. And by solving this optimization problem, we can either generate a feasible motion or certify infeasibility to look for other sequences of actions that can solve the problem. Of course, that means that we have to look for many problems. As you can see, this robot can pick up, grasp that box like this or like that, or many other combinations that I will show in the next couple of minutes. So this creates this huge combinatorial complexity. So for us humans, maybe that's a very straightforward problem, but for robotic agents, all these actions have to be encoded separately. So grasping with this configuration is different than grasping in that configuration, basically. So the robot has to consider one by one which might be the feasible one. So that means we might need to solve many motion problems, basically. And that's not the only problem. So we might also have reachability problems, and we might also have kinematic limit problems due to the joint limits of such robots. And last but not least, basically, we might also have other objects like blocking our grasping motion. And eventually, even for this seemingly simple-looking problems, most actions are actually infeasible. And unfortunately, detecting such infeasibility is often more challenging than solving a feasible problem. So that motivated us to learn a classifier to predict the feasibility of a motion planning problem for a discrete decision directly from sensory signals. For this, and as a next step, we would like to use this classifier as a heuristic to accelerate our search over discrete decisions. So rather than doing some uninformed search in a way randomly, this heuristic will provide us some computational efficiency. But the challenges are how to handle the input dimensionality and how to generalize to different scenes with varying numbers of objects. So again, this is just a kind of a repetition of this nonlinear program. It's just to highlight that how we integrate this heuristic into this nonlinear program. So here we solve again an optimization problem, which depends on the state with some equality and inequality constraint. But here the difference is that we have an action object tuple, A and O, and where A is a discrete action and O is our observation, for example, from visual perception. And these are integrated directly into our constraints as well as our cost function. So then feasibility, we define the feasibility for a fixed action A, where we have the motion planning problem P as a function of the scene, this discrete action A and the observation. Then the feasibility for this specific action is defined as f of s, whereas we define the feasibility of this motion planning for the whole scene, so not just a single action, but all the available actions as f as a function of s and o, which means that there exists at least one discrete action where the feasibility of that action for this particular motion planning problem is feasible. So this is a very deterministic formulation of feasibility of a motion planning problem. But our idea is then to learn a classifier f hat to approximate this feasibility, deterministic feasibility function to speed up this search process over the discrete decisions. But the question is how to encode the scene S, the low level or the high level discrete actions A, and observation as input to the learner, while still generalizing, providing generalization to varying numbers of objects in the scene. So we opt to encode objects in the image space. So basically as a two-channel image, where the first channel consists of a depth image, where we consider all the objects in the scene. And the second channel is nothing but a binary object mask, where we only focus the object itself. So in a way, the mask encodes the object identity. So we capture the objectness, the target objectness, and with the depth image, we encode the geometry of the scene, as well as the relation of this target object to other objects. And our network architecture is also pretty standard, actually. So we use a convolutional neural network to represent our encoded image space, where we also use a one-hot encoded representation for our discrete actions, which are fed into fully connected multi-layer networks. Then we concatenate them to generate this approximate feasibility function as a function of the discrete action and this input image. So for this, we generated data with the scenes and the observations along with this two-channel representation and used the weighted binary cross-entropy loss. So it's pretty standard for such classification tasks. And
these are all in simulation environment, right?
This is in simulation environment, but then I will show we can apply what we learned directly on the real robot.
And what you guys are using, ROS? Are you doing in
no.
ROS gazebo?
No, we have our own in-house developed simulation tool with all the computational tools integrated. So I can talk about this afterwards if you're interested. It's a really powerful tool that Mark has been developing for, I don't know, 10 plus years. And we contribute to that one. Coming back to this visual representation, so as I said, our goal was to use it as a heuristic for the discrete action search. And we use it in two different ways. One is what we call the admissible case. So for this, we evaluate this function for all discrete actions and just pick out the one that maximizes the confidence of that classifier. So in that sense, we pick the one that has the highest confidence in terms of feasibility. Then we solve the motion planning problem with that particular action. And if this is feasible, then we are done. We found a solution with just evaluating a neural network and just picking out one action. So without doing any search at all. But if not, if we cannot find a solution, we just pick up the next one in line, basically. And we follow so until we find a solution or figure out there is no solution at all. So for the feasible problem case, that admissible case usage allows us to only solve a single NLP. Of course, assuming our classifier is pretty accurate. And for the infeasible problem, of course, we have to go through all these actions. So all actions still have to be tested. But that's why it's admissible, because the classification errors, so even if it is not perfect, we can still go through all the actions and figure out that one action might still allows us to find a solution. And the second case is the non-admissible version. So similar to the admissible case, again, we consider the actions, but this time the network predicts infeasibility if for the remaining actions in this list of actions, if we don't have any action that has a higher confidence value above some threshold. So we are trying to be more conservative, if you will, here, basically. Then, basically, if all the actions are below that threshold, we certify the problem as infeasible without doing any solution, actually. So for the feasible problem, then again, we only need to solve a single NLP, assuming a perfect classifier. But for the infeasible problem, that's the upside of this non-admissible case. Since we are being conservative, we might not have to solve any NLP at all. But then this comes with the drawback of that we might increase the false infeasible error metric, basically. Since we are too conservative, we might miss the actions that might actually result in feasible motion plans. So again, coming back to the setup, so the task is to grasp the green box, and we look into the different sizes, positions, orientations of this problem. So it's not a single problem. And we consider different reachability criteria. And we also consider n many boxes obstructing certain grasps. As I try to emphasize, so we have 12 grasping actions for this discrete action definition for just one arm. And since we have two, we have actually 24 actions at all times. And also on top of that, we have 2 degrees of freedom for figuring out exact grasping locations. So here, as you can see, we see different actions depending on which side of the box the robot tries to pick up this green box. So with this, we first looked into single object cases, so without any obstacle objects in the scene. So this is kind of a baseline. It is as if we are reaching out to grasp a box on the table. So we generated data with varying sizes, positions, and orientations of these objects, and with some class imbalance, which we taken into account in our loss function, as well as our test data. So we try to provide a similarly balanced data set here. And for this, we looked into several metrics. The two are the true feasibility rate and the true infeasibility rate. And we consider how they change with respect to this feasibility threshold. So as we can see, we can increase our confidence threshold and achieve pretty accurate results for both metrics. So both of them basically are above 90%. And maybe more interestingly, we look, since we are tackling this computational efficiency, we looked into the number of solved NLPs to find a solution. So when the problem is feasible, on average, we just solve 1.1 or so NLPs. And if we consider the optimal case, we need to solve one NLP. So we are pretty close to an optimal case in that sense, when the problem is feasible. And when the problem is infeasible, then basically we can increase our conservativeness to decrease the number of NLPs that we need to investigate, because these are the times wasted basically, since the problem is infeasible. And with a threshold of 0.5, we actually have on average 0.2 NLPs solved. So for many of those problems, we do not look for any NLP solution at all. But the downside, as I hinted before, of course, once we get more conservative, our false infeasibility rate increases, but we still believe this is negligible as it stays below 2%. And if you look at the computational times, as this was one of our problems, so solving one motion planning problem when the problem is feasible takes half a second to 1 second, thanks to this highly efficient NLP solver. But detecting the infeasibility can take up to 17 seconds. So the more NLPs we get rid of, so not evaluate, as in this case, the more time we gain. And as we see, the classifier query time, including the acquiring the image and encoding it via the network architecture, only takes a couple of milliseconds, which are just negligible. So we also tested this with multiple objects. For this, as I explained, we had a depth image considering the whole scene and the object masks, and we generated many such scenes considering many variations of the sizes and positions. And as we see here, when the action is feasible, we only had to solve just one NLP and got our motion plan immediately. But if we didn't have this feasibility heuristic on expectation, we would have to solve 4 NLPs for this very simple problem. And here, we just slightly changed the position of the green box. Then only this second arm can pick it up. But still, thanks to our heuristic, we only need to solve 1 NLP. But on expectation, for this case, if we didn't have it, we would have to solve 12 NLPs. We also looked into these out-of-reach cases where we didn't have to solve any NLP at all. Similarly, when the box is too large, again, we didn't have to solve any NLP at all. And we also looked into how the varying numbers of objects affect our accuracy. And as we see, with respect to those 2 metrics, our method is pretty robust. So we achieve high accuracies on both metrics, which is independent of the number of objects. And for the number of solved NLPs, it is also robust, as we also have the similar behavior out of this visual heuristic. We also tested this on the real robot. So the training happened on the simulation, but we could actually transfer the architecture directly to the real world case. So here the problem is feasible. And thanks to this heuristic, we would only have to look into 1 action and solve just 1 NLP. But again, without this, we would have to solve 6 NLPs. And this is an infeasible case, which basically we didn't solve anything here. So in summary, with this, we managed to predict the feasibility of manipulation planning problems directly from visual input, thanks to this representation that we generated. Of course, the main assumption was that the scene has to be captured well by vision, so we didn't consider any total occlusions. And we managed to get the generalization to multiple objects with the same architecture. And the number of NLPs is greatly reduced, basically. So, any questions for this first part? Okay, great. So
I have questions. So
Sure,
very
sure.
nice talk, very good idea. Actually, I have a couple, maybe some of them we can leave it to the end.
Sure.
So let me actually skip some. Okay, get to one part. So you are doing like basic grasping tasks. You're treating each grasp as a discrete action, right?
Yes.
Right. But grasping has parameters like where you grasp it from. So I mean, I get it. This is like just an early work, but do you think this can be extrapolated to parts where actually the parameters of the specific actions are also planned over, like parameters of the grasps? Do you see that going there, or does it add extra complexity, or you also need to do like a sub feasibility check for detecting the regions of grasp and then let that handle it, or convert grasping to discrete points of grasps or something like that? Do you think this being easily generalized to that?
So let me rephrase to understand if I get your question. So you mean we can also model or represent the grasping parameters directly via some learning methods? Or
that's what I'm asking, like grasping. I'm not saying you can, I'm asking like, is that how you would incorporate different grasps and generalize it to different shapes of objects? Like instead of boxes, but if you had like cups, forks, like, because like at that point, grasping no longer becomes a discrete action. Like how do you think you would incorporate that into this framework?
Yeah. This is a very good question, actually, which we have been thinking about, especially the last 6 months or so. And we are looking into more implicit representations, like we are trying to understand what are the actual representations that are generalizable for physical interaction. So like you said, if it is picking up a cup, what should be the representation that allows us to plan with respect to this representation directly, and which can also generalize to picking up some other geometrical shape. So there are very small number of work in that sense, and most of them just rely on supervised training, where they label the grasping locations, like the handles in the case of grasping mugs. But I think that's not the way to go. We are trying to understand what are the low-level representational features, like, for example, it could be related to the surface representation, it could be related to some sign distance functions, so that these can be generalized to any object shape. So this is a fundamental question. This is, I think, really a great research direction. Yeah.
I agree. There's actually, some body of work that try to do it in not just labeling, but by interacting with the objects and trying to learn grasp locations. I agree. It's an open problem. So the way you would incorporate that is first pass that through another, like, let's say, classifier, and then find the discrete number of feasible grasp points, and then that's how you would incorporate it as like discrete actions. But then my question becomes like, then you may not be able to represent it as one-hot vectors, right? I was like, or how you would put that action representation inside, or is that what you're saying? Like that would be, the actions would no longer be continuous, or we would have some sort of like a sensory motor vector that's being input to the network to represent actions or action object pairs.
Yeah, these representations could actually be continuous. So we don't have to just rely on the discrete representation. So as long as we can extract the features that we need to optimize or plan our motions, so that's the only criterion. So let's say we have a signed distance function. So looking at a scene, we know at any point in that space what is distance to a specific object, and then this function is differentiable. Right? Then for any object, we can just represent this as a feature and take the derivatives to figure out how to approach an object by using this implicit representation. So we can also learn such representations. There are now scene representation networks, which tries to implement or encode the scene via these implicit representations, which are differentiable. So you don't need to do any discretization at all. It is just about...
But that's no, that's object. I mean, I think I'm taking too much time. Sorry about that. One last point. That's object representation, but you need to plan over the actions, right? So your input to your network would be continuous, and how do you plan over that? That's I mean, I agree, like all of these are interesting questions, but planning wise, how do you incorporate that? Like, do you use now your network is you generate actions somehow, like maybe a generative model, and I feed it to your network, and like a sample-based planning where you use your learned representations as, or like learned models as thing. But I think we can talk more about this. This problems fascinate me. That's why I'm heavily asking questions. Yeah, I think I should yield the floor. Sorry about that, but I'm very excited. Okay. This is really nice work. Yeah.
I think this is a great question, and I can explain how this integration might be realized in this nonlinear program setting. Yeah. I need to dig more deeper to explain it. Yeah.
Just to add to the discussion, I mean, I think it's an interesting discussion from my point of view as well. But you need like a minimum 3 fingers for a stable grasp of arbitrary objects. So with the 2-finger grasper, I think there's a problem. So you can't easily generalize it to arbitrary shape objects. So just from robotics point of view.
Yeah, this is a great input. Yeah, yes, some of our group members look into soft finger architectures.
That might be as well. Yeah.
So thanks for this great questions. I hope we will have time to explain for me to this more deeper later. So for the second representation work, we said, again, our goal is the sequential manipulation planning setting. But now, as the previous one only looked into tackling the discrete actions and generating this black box representation, if you will, here we wanted to have a more explainable representation that not only acts as a heuristic, but also allows us to plan directly on this representation. So basically, we are looking into mapping from images to some representation, and we are also interested in possibly to obtain this representation without explicit labeling signals, and we also investigate the robustness to changes in the environment. So the setting is, again, a pick and place setting. So this is usually the go-to problem setting for that kind of problems. Here, we can see it as a rearrangement problem of different numbers of stacks of objects. So this is the camera image for the robot within our simulation. And we need to plan 2 things again. First, the high-level action sequence to reach from that state to this final state, so a rearrangement of the initial state. And we also would like to plan the robotic motion to interact with the world, to change the environment from this initial state to this final state. So again, we formulate this as a planning problem, as an optimization problem for this planning. And here, our input is basically, for the cost function, is a representation, which could be a latent representation, and these actions, these symbolic actions. Here, the novelty is in this visual module G, which I will explain next, where these visual module transforms our initial scenes to act as the initial constraint, as well as for the final scene. Then we also have an action model, M, which acts directly on this representation and with the predefined action sequences. So we also have this as an equality constraint. So here, what we require out of this state representation Z is two main things. One is it should be invariant. And by this, I mean, it should provide unique mapping of an image to a representation. And ideally, this mapping should be identical between similar images or scenes. And the second property we would like to have is this representation being planning compatible, where we can do goal condition check easily, and also defining the transition rules or actions or learning them should also be easy. Then the research questions are, is there such a form of C that satisfies these above conditions? And if yes, how to obtain them directly from sensory signals? And then last, how to integrate this representation to solve such combined task and motion planning problems. To quickly go over the flow, and the goal scene. And the goal scene could be a symbolic representation. It's just for the sake of argument, I use an image here. Then we transform those scenes via our visual module. Then together with the symbolic action model, we feed them into our planner. This is nothing but a classical graph-based search, which basically figures out the action sequences. These are, again, the high-level discrete action sequences. Then we feed them into the motion planner side. This is where the magic happens. So we extract the low-level robotic actions out of these high-level ones through a just one-to-one mapping. But this is the key part where we extract the geometrical constraints out of these low-level actions. Like for example, for grasping, we extract touch-related constraints, for example, which are then fed into our nonlinear program as action skeletons, which allows us to solve the motion planning problem so that the robot interact with the world to change the environment as we would like. And the novel part is this visual module G, which we train in a fully self-supervised manner. And the idea is that given an input scene image with the stacking of objects, we partition them for each object. Basically, we create this mask, each of which are fed into a shared coordinate regressor or position predictor, if you will, which we call as phi. Then these predictions are fed into again a shared affine grid sampler to basically transform some initial belief of these object masks to generate a transformed version of these objects individually. And as the final step, with these individual transformed masks, we can generate or reconstruct the scene image. And since both this rho and pi are differentiable, we can backpropagate through this reconstruction error to train those predictors or regressors. So let's skip that. And we just use regular mean squared loss to train this in a fully self-supervised manner. And the first component is the fully reconstructed scene, where we have the ground truth compared to the reconstructed image. And the second component only focuses the object mask itself. Again, we compare the ground truth and the transformed object masks. And now, thanks to this visual module, we can extract out, or we can reconstruct the scenes with a representation, which then we can plan on. With this reconstructed image, we do some clustering, pretty standard things, to generate scene graph representations, which defines nothing but the spatial relations of objects in the scene. So this is very simple representation, actually, which is used in some computer vision tasks for image captioning, especially. Then we define our symbolic action model. So we do not do any learning here. It is predefined, and it's based on this state representation of this scene graph, basically. Then with this initial and goal scene graphs, along with the action model acting on these graphs, we can employ any off-the-shelf graph search methods to extract the high-level action sequences. And we tested this on 2 different domains. The top one is our simulation domain, which is nothing fancy. But on the bottom, we also tried it on more photorealistic environment, where we use Blender engine. So this is just scaled up version of the actual images. Otherwise, they are more photorealistic than they look like here. Then for the evaluation, we trained this Vision Module G only with a data set that contains 5 objects and 3 discrete stacks. And we tested the scene graph representation accuracy. Along with this, we also looked into the confidence score, and we quantified this by the intersection over union IOU metric. So in our tests, so we considered 6 objects in 3 stacks and also 7 object cases. So if you look at the first 3 rows, so these are all unseen scenes basically. We have high accuracy on the scene graph representation, which are close to 90%. And we also have high accuracy on the confidence of that mapping with the IOU metric. We also tested the robustness by changing the camera view slightly and somewhat significantly. And here, even though our IOU metric decreases significantly, we observe that even with this accuracy, our SG accuracy, so constructing these spatial relations, are still high. Then we are still able to do planning even when the view changes around that degrees. So these are some planning samples. So far left, we see the initial conditions, and on the rightmost column, we see different goal conditions. So we can tackle n many goal conditions, and our planner comes up with basically the action sequences that results in generating these goal conditions. We also extended our work to 3D, and by 3D, this is not again full 3D, it's discretized. So, but we introduced a second row of stacks, and again, out of the box, we can employ our methods. This time we introduce, of course, another spatial relation, like behind or in front, and still being able to constructing such scene graphs to do planning. So these are initial settings, these are final settings, and these are the intermediate actions we take to reach this final goal. And as a secondary extension, we also looked into integrating some heuristics, especially the stability heuristic. For example, by integrating some object classification. So at the bottom, we see the case where we don't employ the heuristic. So we have these spherical objects, and the intermediate states might involve cases where we have to place some rectangular boxes on top of those, which are likely to be unstable. But once we integrated the stability heuristic, as we see at the top, we can avoid such unstable action sequences, basically. And surely we employed this on the robot side by integrating it with the motion planner. And the action sequences come from the visual planner. And our NLP solves the motion plans by constraining on the physical constraints. So with this, to sum up, we managed to get an invariant representation, but the robustness is not fully captured yet. So, but it's definitely planning compatible, as we see from the examples. So maybe time is running out. So this is the second work that we focused on representations that allows us to do planning for robotic sequential manipulation. So for the next part, I would like to focus quickly on the motion planning part. And for this, our target is long horizon tasks, where we need to tackle hundreds of sequential actions to realize a final goal. For this, we take this architectural construction case study, where we wanted to build this pavilion. So this is an actually built pavilion a couple of years ago in Stuttgart. So we would like to see if we can build this pavilion fully autonomously via our formulation. So we have two robots. One is a crane on the left, which has the capability to pick up the pieces. The other one is a mobile manipulator, which takes the pieces from the crane and places on the goal locations. So we would like to go from this initial layout to this final design. So the idea is to solve only a subset of problem at a time. So this is not a genius idea, of course, but the problem is how to determine the sub-goals. So for this, we consider two decompositions. One is only considering a limited horizon setting. So basically that means only looking into placing maximum number of pieces at a time, like 4 or 5 pieces at a time. Then the second part is introducing some domain-specific metrics to guide the high-level decision-making, which I will explain quickly. So for these metrics, we define a statics metric where we compute the average torque, basically. So whenever we try to, or we imagine to place a piece, we compute the average torque over the whole building currently being built. And these torques are computed by solving for the static equilibrium conditions. So these are just approximations. So this is not like fully accurate metric actually. For the second one, we consider the neighbors metric. So basically we try to maximize the number of neighbors for the piece that we would like to place. So this is computationally simpler, of course, but it is not as accurate as the average torque one. So if we compare what each allows us to do, so on the left we see the goal configuration. So basically constructing an arch where 2 pieces are already placed. So if we rely on the statics metric, we would have to choose placing this red block so that the average torques are minimized. But for the neighbors metric, it's equally likely to place either this red box on the floor or this uppermost one here, which would likely to create more torques on this half-built arch. So, and on the motion planning side, we also introduced these lower bounds. I will quickly skip over them. So the first one relies on these metrics. So if we cannot find an action, so basically this representation defines this lower bound. And by lower bound, I mean if PI is infeasible, then PI plus 1 is infeasible as well. So with this decomposition, first we try to find solutions where we minimize the metric that we would like to use. Once we found this, we switch to the next decomposition, which is finding the final poses of the objects, so without any motion. Then if we find a solution, we switch to the other decomposition where we find keyframes, like only the keyframe of picking up the wooden block, or handover keyframe, or the placement keyframe. So once we find solutions also for these keyframes, then we pass on to either a sampling-based motion planner or our NLP directly. So I will skip directly to the results. So with this, we evaluated those metrics, and dark parts are placed first, and light parts are placed towards the end. And on the far left, we see the original order used in reality, like in building this pavilion, defined by the engineers and architects. And this is kind of the second one, is our kind of baseline, where we don't utilize any metric at all. So the only condition is to select a part is whether there is a neighbor already placed. So then this creates an almost random ordering. Then if we look at the neighbor metric, we see some structure is evolving. First, these basically support structures are built, and then the intermediate parts. And when we look at the statics metric, then we see even more structures occurring, and it gets similar to the design that's actually used in reality, which is encouraging. So of course, this was not only solving the sequences. While doing that, we were also checking the feasibility of whether we could plan motion trajectories to realize these sequences of motions. So eventually, with these decompositions, we managed to generate sequences along with the motion trajectories to fully construct this building from zero till the end, fully autonomously, as we see here. So, but this, of course, so with this, yeah, we did this task decomposition on 2 levels with limited horizon and domain-specific metrics. And we combined sampling and optimization-based methods for robustness. And we tested this on real architectural buildings. But the limitation was that it is not trivial to scale for multi-agent systems. By multi-agent, I mean more than 2 agents, due to scheduling and synchronization of actions, basically. And in this very recent work that we just submitted recently, we tackled this problem. So now we can have like 8-10 agents that collaborate together, of course, to build, again, such long horizon tasks. We again focused on some construction or assembly settings. Now this time we not only decompose the task, but we also consider the decomposition in terms of agents. So during this scheduling part, we only look at available agents in a way, which allows us to also distribute these tasks effectively. We also introduced some time-embedded keyframe optimization and a novel bidirectional space-time motion planner based on an RRT planner. And we integrated all these into a single architecture where we can solve robustly from start to end fully autonomously. And we consider different cases and we also consider different robots to see the generalization and robustness. And just a quick single metric analysis, which is of interest to us. Basically, in the ideal setup, the more agents we include in the scene, we would like a linear speed up increase in terms of the execution of this task. But this is an ideal case, of course. But in reality, this is what we observed. So we believe this is still quite good. Of course, after some number of agents, we get diminishing returns because as we see also from the 2 examples, for example, we consider a tower example where the physical field is very confined. So the more agents we have doesn't help us much. But for the wall scenario where we have a much wider case, our gains are much better. Of course, again, we managed to utilize, I think in that case, 8 agents to fully build another pavilion. This pavilion is now in the design phase, but I think it will be also fully constructed towards the end of the year or so. So with this, we managed to figure out not only the sequences of actions, but also the motion trajectories of all these agents. And hopefully the architects and engineers will try to use the sequences that we provide here, or at least they will try it. Yeah. And here at the bottom, we see the scheduling over these 8 mobile agents with different actions that they employ at any given time. So we see a good distribution of tasks, basically, and not losing much time. So yeah, I will skip maybe the learning part. Yes, we also have some safety reinforcement learning on the real robots. So maybe just wrap up. So where are we? My goal is to tackle this autonomous physical reasoning tasks so that the robots can actually be employed in the real world next to humans, hopefully. So today I didn't talk about my PhD, but my PhD was all about human-robot interaction. So in the near future, I would like to combine what I described today with my PhD know-how. So basically, I am kind of proposing a new kind of intelligence, but actually this is not so new. So as I try to emphasize, I think we have the necessary tools. It is just about how to get them integrated in a principled way. And for me, the objectives are then clear, like acquiring representations from sensory signals. This could be also haptic signals in the future, and also decomposing such long horizon tasks into solvable units, and also integrating learning and control to tackle the uncertainties or adaptation to unseen situations, basically. So with this, I think I finalize my talk, and here are my collaborators, mostly from my postdoc work. Yeah. Thank you.
Thank you, Ozgur. This was really a very interesting talk. And I think we can now have some questions. So anyone who would like to ask a question, you can just unmute yourself and ask your question.
Maybe I can start by, I think Metin Hoca asked this question, right? So he was asking about this, how to integrate representations in a more generic fashion. If I summarize it quickly, so the idea is that this logic geometric program that I tried to really explain in a hand-wavy manner relies on feature representations. So by features, I mean features that depends on the state. For example, one feature could be the distance between two objects. Right? So if we have access to the state of the environment, then within this architecture, we can construct these features that are fully differentiable. So then if I know where my fingertip is, and if I know where the object is, and if I know the mesh, the 3D representation of this object, then I can compute such features. And these features are a function of the state, and these features are at least twice differentiable. And because actually this constraint optimizer, it's called k-order motion optimizer, and this k-order means we can have k-many differentiability depending on the feature. So when we have these features, we can generate motion quite fast. And we have features and this feature set is actually remarkably not that big. So with 10 or 15 or so many features, we can generate all these interesting behaviors. Because apparently, if you think a lot about these physical interactions, many of them, for example, relies on this touch-like behavior, whether it's a grasp, whether it's a push, whether it's a slide or pull. For example, this distance feature used in all these more high-level constraints. So basically what these features define, they define two things. They could define cost functions, or they could define constraints. So I can also define a touch constraint which depends on this distance feature. Then this touch action skeleton, we call them skeletons, or skeleton entries, maybe more appropriately. Then this touch skeleton entry defines a constraint, which means the finger endpoint should be at the surface of that object. And since we know the distance feature, and since this is differentiable, we just differentiate these decision variables, which are the degrees of freedom of the robot, to move this endpoint closer and closer to this point to satisfy this constraint. So with this, I don't know, again, a little bit hand-wavy explanation. So if we can generate such features out of representations, this is why I gave this sign distance example, because for such features, it is a perfect match. We can just extract out these features and plug it into our nonlinear program.
Actually, I was going to ask you something similar to this line. So in the second part about this motion planning project, you mentioned that you introduced some sort of heuristics about physics. So can you also try to learn these maybe in a more symbolic manner from the observations, directly from the vision input, maybe before and after action pairs?
This is also a great question, and this is, I think, might be the first question I asked when I joined my postdoc group. Apparently, this is not easy. So we still couldn't figure out how to learn such symbolic representations via exploration. So it sounds promising, but yeah, we couldn't figure out how to do it in a systematic way.
Thank you.
I had a quick question too, if you have time. Ozgur, when you do these simulations, you're effectively sampling your space, right? I was wondering if you looked into how finely that space needs to be sampled, and if there are, strategies for controlling the level of sampling that you need eventually. So I'm not sure if you talked about that.
You mean sampling in terms of high-level actions or sampling in terms of motion planning?
Well, you're generating these paths, right? You're generating these sessions in simulation world, right? And they explore different parts of your space, your action space. And the more you run those simulations, the more samples you're getting. So what I'm asking is really, have you looked into, the marginal benefit of exploring that space further and further? Like how many explorations or how many sessions is sufficient? Is basically my question. This is in part because I'd like to get an idea of to what extent your learning mechanism is able to learn or generalize from the examples that you have, as opposed to having a learning setup where you've already generated every possible state in your simulation and you're maybe doing some nearest neighbor like classification or in your learning parts.
Okay, I think your question is mainly about this representation work, where we, let me try to get back to it. Maybe that one. So here, yeah, we consider all combinations for the training. Let me try to find. For the training, we consider all possible combinations of 5 objects and 3 stacks. So this is kind of fully explored. We just test it on different number of objects to see if it is kind of transferable to different scenes with different number of objects. So in that sense, our focus was not about whether we are wasting resources or time to fully model this. Our goal was mostly to see if we can utilize this self-supervision, so that if we employ robots in the real world, hopefully they can do this self-supervision by themselves for any given scene and build their representations autonomously. But of course, in that sense, that's a good question, which we didn't investigate it. Like, what is the minimum requirement to get a representation through exploration or through basically taking into account different sets of scenes? This is not something we looked into, but if you also ask whether we explore in the motion planning domain, maybe I misunderstood that part. We don't do exploration in the motion planning phase. It is just fully deterministic in the sense that we just solve the optimization problem. But of course, to transfer that to real world, we then incorporate these motion plans with some reinforcement learning architecture to learn generalized policies For that one, we investigated how many episodes we need. But yeah, maybe I should go deeper in that one. I don't know if I was able to answer your question.
Thank you.
So.
Okay, I think we can stop here. Again, Oz, thank you for accepting our invitation and giving this interesting talk.
Yeah, thanks a lot for the invitation, and it was nice to see or talk to you, all of the professors who basically encouraged me to follow this career at the first place. Yeah, thanks.
Okay,
thank you.
Nice seeing you.
Thank you, Ozgur. Thank you for the talk.
Yeah.
For the nice talk.
See you.
Have a nice day.